a functional camera, which is not.
Was it a new one?
It's a new camera, and it was zoomed properly when I set it there, but now it isn't, so I don't know. I'll never get this to work. Okay. So the water cycle, or the hydrologic cycle, we see water moving from different parts of our environment. Where is the vast majority of the water on Earth found?
The ocean.
The ocean. The vast majority, 97 point something % of water is found in the ocean on Earth. Is that fresh water? Salt water. So are we able to drink salt water and use it for lots of purposes? No.
Nope.
So most of the available liquid water on Earth is in the ocean, and it's salt water. But of course it's hugely important for us because of the plants that live there produce the majority of the oxygen that we need, fish that live there, the way that such a vast amount of water controls temperature on Earth and weather. The ocean is increasingly understood as super important in so many ways to life on Earth. And then, liquid water-wise, where do we find the next largest percentage of water?
Glaciers and
Liquid water-wise. So Joshua.
Liquid water.
Well, the ocean is liquid water, right? It's salt water, but it's liquid. So what's our next biggest source of liquid water?
Lakes, rivers.
Groundwater. So groundwater. And what do we know about groundwater? How much water is groundwater?
2 point.
That's good, but that isn't liquid water. That 2%-ish number is
Glaciers and icebergs.
glaciers and icebergs. That's solid water.
It's like 0 point something percent.
Yeah, it's like the tiniest, and we'll go over and write these down on the lab sheet later. But groundwater is like 0.685%, like a tiny fraction, of like just over half of 1% of the water on Earth is liquid fresh water found in the groundwater supply. That's the biggest, and there's a really tricky question on the test, so I don't want any of you to be fooled. If it asks you about the biggest source of fresh water on Earth, what would that be? Glaciers are the biggest source of fresh water because they are made of fresh water, but they are solid. They're frozen. If you're asked what the biggest source of liquid fresh water on Earth is, groundwater. So be really careful to note, are we talking about any fresh water, or are we talking about liquid fresh water? It's a very key point to understand. So 97.2 something percent is saltwater, ocean. Then that just little bit of water left, the biggest reservoir of that we have is freshwater, glaciers and icebergs. And we'll talk about how they're made and that later. Then groundwater, we have here, groundwater, just a little bit, but the biggest source of liquid fresh water on Earth, 0.685% of the total water on Earth. And then we have things like lakes, rivers, surface water, not underground like groundwater, but surface water is just a tiny fraction of what you have, and soil moisture, which is liquid fresh water. And then, how about gaseous water, water vapor? Where do we find that?
Atmosphere.
In the atmosphere. And that's like the smallest net amount of water on Earth. It's like 0.001% is in the atmosphere. And of course there's water vapor making up clouds, water vapor just here in the air that we don't see, but we certainly can tell when the day is humid. There's a lot of water vapor in the air. Makes us feel hotter than we would otherwise. When it's very dry, the sun gets terrible nosebleeds, you feel thirstier, you feel like your skin is parched. Maybe you guys are young, but when you get older, your skin will be like, oh, when it's very dry in the winter. So humidity, even though it makes up such a tiny fraction of all the water on Earth, is very important to us in our comfort. We notice it definitely. So when you talk about the water cycle, you see all of these different places where water is contained on Earth are connected to each other. All that water in the ocean, 97.5 something percent of all the water on Earth, does it stay in the ocean? If it's in the ocean, it just has to stay there? No. What can happen to that water?
It can evaporate.
It can evaporate. So when water evaporates from the ocean water is salt water, right? When it evaporates, does it remain salt water? No. When water evaporates, it goes from a liquid to a gas that takes energy. But all the salts that are dissolved in that water don't evaporate. They're still solids. When something's dissolved in water, it's still a solid. So it's not even becoming a liquid, much less becoming a gas. So when water evaporates, it's just the water molecules that go into the air, not the things dissolved in the water. So it becomes fresh water when it evaporates, right? So when water evaporates from the ocean, what could happen to it next? So many paths. So Ryan, tell me one thing that could happen to it.
Evaporate? No.
Once it's evaporated, it could,
Rain?
yeah, it could become a cloud. So when water vapor evaporates from the ocean, then it becomes a cloud. What happens to it?
It condenses.
It condenses. Okay, so if we have water vapor evaporate from the ocean, become a gas, then it condenses as a cloud, it's become a liquid again, right? Some clouds that are up very high, which we'll learn about in a couple weeks, also are just made of ice crystals, so it can actually even become solid, depending on the type of cloud we're looking at. But these big puffy clouds are made of liquid water, so the water can go from liquid to gas, then from gas back to liquid as a cloud. And then what could happen to that cloud, Meredith? What does a cloud do?
Rain?
It could rain. Okay, so then that cloud is condensed, it's now liquid water. Then that liquid water could fall to the earth as rain or snow, depending on temperature and such. It could fall over the ocean and become part of the ocean again. Could fall over the earth. If it falls over the earth, where might it land, Patrick?
Ocean, rivers,
Okay, might land in a river, might land...
lake, turn into groundwater.
Okay, so it could turn into surface water, fresh water. It could fall on the soil, become soil moisture. And then if it was going to become groundwater, Joseph, what would happen to it once it rained onto the ground?
That was like absorbed water.
Right, so groundwater sometimes gets absorbed by tree roots and used by a plant, right? But sometimes, if there's enough groundwater, sometimes it'll get all the way through the soil into the actual groundwater supply. So there are all kinds of options. It could, if it fell into a lake, it could evaporate again, become a cloud, start all over. Could just stay in that lake for a long time. Could become a stream.
I thought I read that it says if it rains into the ocean, its chances of being evaporated are like every 1,000 years it'll get re-evaporated or something like that.
So that brings us to the concept of what? What is it? How long a time something's going to be? Joseph? Residence time. So, residence time. If you think about even people, we kind of have a residence time, which maybe people who live around here are more aware of than people who live in other places. Where I grew up, nobody ever moved there and nobody ever left. It was kind of what it was. The residence time for people in the place where I grew up was long. You were born there, you lived there, you died there, that was it. Nobody came and nobody left. I mean, we got like maybe 1 or 2 new kids at my school the whole time I went to school. And nobody ever left. It was just a place where if you lived there,
So
you lived
what
there.
happens to the first grade in kindergarten in preschool?
Well, I mean, more kids are born each year, but, families don't move in, families don't move out. It's like residence
Like
time is...
like you said, nobody else was coming into the school.
well, people get born, but they don't, new people don't come in.
People from
So,
other
The
areas.
preschool would be like gone.
residence time is long. Here, right, residence time is probably like every 3 years because of the military base, right? You have a 3-year tour, people come, people go. Residence time maybe average 3 years. People come, people go. It has a much bigger turnover. So, when you consider residence time for water, you have to consider how fast the place where the water is can move. You have to consider what kind of exits and entrances you have to that place, and you have to consider the net size of the place. Okay, so kind of some guidelines for residence time. A smaller amount of water will probably have a faster residence time. A larger amount of water will probably have a longer residence time. If you consider the state of matter, most residence time for gases tends to be shorter than for liquid and shorter than for ice, solid. Large bodies of water, like the ocean, tend to have very long residence times, whereas smaller bodies like creeks have shorter residence times. Moving bodies of water, like rivers, have short residence times compared to totally stagnant bodies of water, like lakes. So residence time, just how long water tends to stay in a place. Especially water molecules that live at the bottom of the ocean, very unlikely they're going to exit the ocean ever. Say a lake that has an outflow to the ocean and an inflow here, do you think it's likely that water would eventually leave the lake and enter the ocean? Yes. Yeah. How about a lake like the Great Salt Lake where things flow in but there's no way out? What's the only way out for that kind of water? Evaporation. So that does happen, but certainly less water will be evaporating than if it could just flow right out. So its residence time, probably the Great Salt Lake has a residence time that is larger than a lake that has a way out, a stream that leads out either to another river or an ocean, at the same temperature. Of course, a lake in a hot place would have more evaporation at a higher temperature. A lake in a cold place would not have as much evaporation because cold air holds less water vapor than hot air. So you can see the water cycle. And if we look, and we will, in the lab here, look at all of these things more carefully. You guys know evaporation is water going from what state to what state, Max?
It's going from a liquid to a gas.
Yes, do you have a question?
Yes. Why would like an ocean have a longer residence time than like a lake?
Because the surface area of the ocean is small compared to if you think of the depth of the ocean, there are so many water molecules that just don't have a chance to evaporate because they're way down there in the deep part of the ocean, whereas a lake has a much bigger surface area to volume ratio, so they get more of a chance to come to the surface and evaporate.
Is the residence time for the ocean like average? Because it includes the ones on the way top and the bottom.
Yeah, shallow areas of the ocean, if your water molecule's there, it probably has a better chance of getting out. Hotter areas definitely have a better chance of having evaporation. There's not really a whole lot of chance of evaporation when it's cold and deep. that's lowering your odds, but molecules do still evaporate. I mean, even like if I take the lid off here, even though it's not at its boiling point, of course, some water molecules get collided with enough that they get enough energy to evaporate. That's why if I left this here long enough, the whole thing would eventually evaporate, even though the room is cool compared to the boiling point of water, right? Because every now and then, especially if I give them extra energy, right, one molecule will get enough speed to evaporate, and it will. All it takes is a certain amount of energy for that one molecule.
How would it get to this room? Like,
Tell me again.
how would whenever it evaporates, how would it go straight to the home so they want
No, it would just become water vapor in the air, humidity.
Okay.
So Water has a better chance of evaporating in a low humidity room, like here. In the summer when the humidity is high, if we turned off the AC and we had high humidity, it would have less of a chance of evaporating. So it's kind of playing the odds a little bit for each molecule to evaporate. So when it goes, whether it's fresh water or salt water, when water goes from liquid to gas, it evaporates. When it goes from gas to liquid, it does what? Condenses. So condensation can happen in cloud formation. It can also happen, like say I had an ice cold drink sitting here, right? Occasionally a water molecule would crash, a water vapor molecule would crash in from the air. When it hit that cup is cold, it would rob it of energy, right? Because you know energy, heat is a consequence of transfer of energy. So when a water vapor molecule hits a cold thing and it loses energy to the cold thing because it's hotter, then it might condense because its energy is decreased. So that's why the outside of your ice cold cup collects liquid, right? That's why you need to use a coaster, because then it will drip down and make a puddle on your table because condensation. So water vapor can leave the air by hitting something cold. It can leave the air by forming a cloud. It can leave the air by precipitating, and then it becomes a liquid again. One other way that water vapor can get from the ground into the air is transpiration. Does anyone know what that is? Stephanie?
The transfer from plants to the air.
Right.
Well,
So for our little experiment today, which we really need to get started, we have this sad little plant here, which perhaps will transpire for us a little bit. So transpiration is when a plant's roots absorb water, the plant uses that water. When a plant makes its food, you'll learn in biology next year, it takes carbon dioxide and water and produces sugar and oxygen. And it can give off water vapor when it has excess water as it lives and goes along. I'll plant this little guy in here. I'm hoping to kind of create a little mountain over here too. Like a little fake world for us in this jar. So we definitely need to get started or we won't have any time to see anything happen. So would you pass the lab sheets, please? Thank you. So we're going to look at the water cycle here carefully and we haven't talked about freezing at all yet in the hydrological cycle, but we will. I have a little cup full of table salt right here. Beaker full of table salt. I'm going to make a concentrated solution here. I don't know how much water it will take to make us a little ocean in here. Of course, the ocean is salt water. Now, is table salt the stuff that, oh dear, I'm passing out. Yeah, there are at least two kinds of worksheet. At least two kinds of worksheet. We're having some confusion. Alright, if you don't have two different worksheets, you need to get them, but next week we'll be doing this. So make sure you get one and make sure you bring it to class next week. The back of today's lab sheet will also be done next week.
You're going to want to use
this. Okay. You can see disaster happening. Oh, right, good plan. I was figuring on spilling everything on it too. Okay, so you know that the ocean is salt water, but does that mean that the salt in it is table salt, like sodium chloride, like what we put on our food?
What was the question?
The ocean we call salt water, but we call table salt salt. But is table salt the only kind of salt in the ocean?
No.
There are many kinds. The ocean has many kinds of salt in it. Salt, for a scientist, is just an ionic compound. It has a metal and one or more non-metals. Salt has the metal sodium and the non-metal chlorine, table salt. But other salts can be made of other metals and non-metals also. And there are many of those. Because last week we looked at ionic compounds and polar compounds, and how both of those dissolve readily in water, right? Polar things and ionic things dissolve readily in water. So I'm going to make us a little ocean here with our salt water. I'm going to have to add a little water to it too. This water is already salty also because it's the leftover of the stuff that we made the composition of water, the electrolysis of water, the baking soda water. So that's a whole different kind of salt. Baking soda is also a salt. It's not table salt, but it is another kind of salt. So now we have a little ocean. We have some sand, we have some dirt, we have our little plant, a little mountain. So if you want, try not to like shake the jar so that our little mountain gets underwater, but pass it along, have a good look at it, and we're going to draw a little diagram of it. So I made strong salt water and added it to the jar. There's some dirt, a little plant in the bottom. And as soon as you've all looked at it, we're going to cover it with plastic wrap and close it with a rubber band. Put it in a sunny window and see if we can observe the water cycle.
So do we draw it here?
Yes, so you're going to draw what you see in the jar. Maybe you've got a jar. That's a terrible jar. That's sand. Little mountain. Water. Okay, so I'm going to cover that with plastic wrap held on by a rubber band. So now, hopefully,